Hello, in this video I'm going to be going over some basic quantum mechanics where we look at the energy found in electrons within an atom. We do this using Bohr's model, and we have to know that light has a dual nature, meaning it acts as a particle, meaning it has some bit of mass, and it also acts as a wave, just like light in the electromagnetic spectrum. When looking at it, we have three different series. One is called the Balmer Series, and that's the series we're going to focus on. And it's basically, no matter what energy level an electron is at, as it jumps down from one to another, like 6 to 2 or 4 to 2, 2 is the ending point. So drawing it, we have 1, 2, 3, 4, 5, and so on. N equals 1, 2, 3, 4, 5. So we could have a drop from 3 to 2, it's going to release energy in the form of light. Or we could have a drop from 4 to 2, it's going to release more energy in the form of light. From 5 to 2, it's going to release a different wavelength of energy in the form of light. And so on, 6 to 2, 7 to 2. All of them end at 2. And what it does is it's going to produce a line spectrum. You have violet blue, green blue, orange red, and that is the Balmer Series. The next one is the Lyman Series, and for this, all of your jumps are ending at n equals 1, energy level 1. And for this one, the line spectrum is going to be found in the ultraviolet spectrum, so we can't really see it with our eyes. We'd have to use very expensive machine. Then we have the Paschen series, and this one is where it ends at 3, n equals 3. And for this one, the line spectrum is going to fall into the infrared. And the infrared has a lower energy than the ultraviolet. So, flipping over to do a problem, we have a question, and we have given, these are various wavelengths in nanometers, for the various frequencies or colors. It says draw arrows to represent an electron dropping from the 4th to the 2nd energy level. What wavelength and color does this wavelength or does this light represent? So here's n equals 1, n equals 2, n equals 3, n equals 4. So 4th to the 2nd. Here's the 2nd, there's the 4th. We're moving down here. And it's releasing energy in the form of light. We need to figure out what wavelength this is. So we look back at the data on this guy, Balmer Series. So 4 to 2 looks like it's green/blue 486. Which is green/blue 486, blue-green. Alright, next question. Calculate the energy associated with this change. So we want to find the energy. So we're going to have to use maybe one or maybe two of the equations. Here's the wave model. It says that wavelength times frequency equals the speed of light. And here's the particle model. The photon of the electron, or the energy of the photon, equals Planck's constant times frequency. Alright, so in order to answer this question, it says calculate the energy associated with this change. So energy of the photon equals Planck's constant times frequency. We don't have the energy, we don't have the frequency. All we have is Planck's constant, which is always 6.626 times 10 to the negative 34 joules times seconds. So it looks like we're going to have to do the wave model first. Wavelength times frequency equals speed of light. Speed of light is always 3 times 10 to the 8th meters per second. Frequency we're not sure, wavelength is given to us. So we have wavelength times frequency equals speed of light. Alright, so 3.0 times 10 to the 8th meters per second equals frequency, and our wavelength is 486 nanometers. However, we're in meters. So we're going to have to convert our nanometers into meters. Alright, so I'm going to write down 486 nanometers. I'm going to times it by what I want, which is meters. I'm going to get rid of what I don't want, which is nanometers. And I'm going to put 1 on top. So I always like to put my number 1 with my larger prefix. And I have to figure out, alright, how many nanometers are in a meter? Well, if you don't have it memorized, you can always do that. King Henry died by drinking chocolate milk, making Nancy pout. We're at nano. We're going to milli. That's 3. Milli to, sorry, that's micro. Micro to milli is 3. Milli to centi 1, centi to deci 1, deci to base unit, which is meter, 1. So that's 3 plus 3 is 6, plus 1 plus 1 plus 1 is 9. So we're moving 9 steps to the left. 1 times 10 to the 9th. So really, to solve this, it's going to be really helpful to pull out our calculator that we always bring to class. So it's really not that big of a deal. 486 divided by 1 e to 9th. E stands for times 10. And the E button is right here. It's actually called the EE button. So I just typed in 1 E 9. Stands for 1 times 10 to the 9th. Alright, and that gives me, let's count those zeros, put those in the video so you can see it. Basically, it's 4.86 times 10 to the 1, 2, 3, 4, 5, 6, 7. Negative 7. So that's how many meters we're dealing with. And it's negative exponent because our number is less than 1. Alright. So, plugging this into our equation, wavelength times frequency equals speed of light. Plug it right in here, 4.86 times 10 to the negative 7 meters. Pull our calculator back out. So 4.86 e negative 7, oh bummer, 3 e to the 8th. And I'm going to divide both sides by 4.86 e negative 7. And that means my frequency is going to be 6.17 times 10 to the 14th hertz, also known as 1 over seconds. Same thing as hertz. Alright, next what I'm going to do is I'm going to plug it into the energy equation. So my energy of the photon equals Planck's constant, which is 6.626 times 10 to the negative 34th, and just double checking, 6.626 times 10 to the negative 34th joules times seconds. And we're going to multiply this, and I didn't give myself enough room, but 6.17 times 10 to the 14th, 1 over second, which really means seconds cancels out. We're going to be left with joules for our overall answer. Times this by 6.626 e negative 34 gives me 4.09 times 10 to the negative 19 joules is the amount of energy that this wavelength of light has when you move from the 4th to the 2nd energy level in the Balmer series for the element hydrogen. Alright, this next question, do the same for an electron dropping from the 6th to the 2nd. What wavelength and color is this light? Alright, so in this case we're going from the 6th energy all the way to the 2nd energy, and it's emitting light, energy in the form of light. So, with the information given, what we can do is we can do an equation that will allow us to find the energy when we just have the upper energy level and the second energy level of this jump. The equation that we're going to be using is, we've got energy equals hv, which also equals the Redbird constant, which is a new constant, which you'll be given on the test, and it's times 1 over n squared lower minus 1 over n squared upper. And basically, you need to make sure that you have your bigger number minus your smaller number so that it is positive. Alright, so what is the Redbird constant? The Redbird constant is 2.18 times 10 to the negative 18th joules. We're going to multiply this by 1 over n squared lower. Our lower is our 2 squared minus 1 over our n squared upper. Upper is being 6 squared. Alright, and 2 squared is 4, so that's really like 1/4. And what's 1/4 equivalent to? It's going to be 0.25. And then 1 over 6 squared. 6 squared is 36. So 1 over 36 is 0.028. We'll round it to. .25 minus 0.028 gives us 0.222 times it by our 2.18 times 10 to the negative 18th joules, and that's going to be giving us our energy. Alright, so I'm multiplying this out, 2.18e negative 18. So that gives me an energy of 4.84 times 10 to the negative 19th joules is my E. So if it were the question we're asking you, what is the energy of this photon or this light being emitted, that would be my energy. However, it's saying what wavelength and color is this light. So I need to find a wavelength so that I can then determine which color of light it is. Okay. So, what's another equation for energy? Well, energy equals Planck's constant times frequency, and then wavelength times frequency equals the speed of light. So I'm going to have to go back and use those two equations. So this is as tough as it gets. Planck's constant, remember, is 6.626 times 10 to the negative 34th joules times seconds, and you will be given that on the test. Don't have to memorize it. And our frequency is what we are going to be looking for. So then, I take my energy and I divide both sides by 6.626 e negative 34, and that's going to give me 7 for my frequency, 0.30 times 10 to the 14th hertz, or 1 over seconds. Once I have that, I can plug it into wavelength times frequency equals speed of light. So my wavelength times my frequency equals my speed of light, 3.0 times 10 to the 8 meters per second. I'm going to divide both sides by my frequency, so 3e8 is 3 times 10 to the 8. Divide both sides by 7.3e14, and that gives me a wavelength of 4.11, 1, 2, 3, 4, 5, 6, 7 times 10 to the negative 7, which is also 411 nanometers, which when I compare it up to here, it's pretty close to 410 nanometers up here. So my color would be violet, my wavelength would be 410 nanometers, and that is just a taste of quantum mechanics.